Hello everyone, my name is Haoyuan Zhang. Today I will present our work From Intuition to Investigation, a tool-augmented reasoning MLM framework for generalizable face anti-spoofing. In this work, we explore how to enhance multimodal large language models for face anti-spoofing by enabling them to actively use visual tools during reasoning. Face recognition systems are widely used in real-world applications, but they are still vulnerable to presentation attacks, such as printed photos, replayed videos, and 3D masks. Recently, MLLM-based face anti-spoofing methods have shown promising generalization by generating semantic descriptions together with binary predictions. However, these descriptions are usually coarse. For example, the model may only say, "This is a face wearing glasses," or "This looks like a mask," while missing subtle spoof traces. A key limitation is that MLLMs often have some blindness to low-level visual features, such as abnormal texture, frequency artifacts, or unnatural boundaries. These fine-grained clues are very important for robust and generalizable face anti-spoofing. So our question is, can we guide MLLMs to move from intuitive semantic judgment to deeper visual investigation? To answer this question, we propose TAR-FAS, a tool-augmented reasoning framework for face anti-spoofing. Our contributions are threefold. First, we reformulate face anti-spoofing as a chain of thought with visual tools paradigm, where the model can adaptively invoke external tools to inspect fine-grained spoof evidence. Second, we construct Tool-FAS 16K, a multi-turn tool-use reasoning dataset through a tool-augmented annotation pipeline with expert model guidance and verification. Third, we design a tool-aware training pipeline, including FAS knowledge transfer, tool call format injection, and diverse tool GRPO, enabling the model to autonomously learn effective tool use. Now, let me introduce our dataset construction. We build Tool-FAS 16K from Celeb A spoof. It contains 16,172 samples, covering real faces and 10 spoof categories, including photo, poster, pad, phone, PC, face mask, upper body mask, 3D mask, and region mask. For each image, we use Gemini 2.5 Pro to generate multi-turn reasoning trajectories. During annotation, the model does not only give a final answer. Instead, it can first think about the image, call a visual tool, observe the tool result, and then decide whether more investigation is needed. To improve reliability, we introduce expert model guidance. Lightweight expert classifiers provide spoof probabilities for tool outputs, and the annotation is further checked for correctness verification, format verification, and manual verification. This slide shows the overall TAR-FAS framework. Given an input face image, TAR-FAS first provides a fast answer, including a real or spoof classification and a short description. This is similar to an intuitive judgment. However, when deeper reasoning is required, TAR-FAS starts a multi-turn investigation with visual tools. The toolbox includes several complementary operators. The zoom-in tool focuses on local facial regions. The frequency tools, including FFT and wavelet, help detect artifacts from screens or printed media. The structure tools, such as HOG and edge detection, capture unnatural contours and boundaries. The texture tool, LBP, analyzes local texture irregularities. By combining these tools, TAR-FAS can inspect subtle evidence that is difficult for a standard MLLM to perceive directly. The training pipeline has 3 stages. The first stage is FAS knowledge transfer. We train the general MLM with face anti-spoofing data so that it learns basic domain knowledge and can produce a fast classification with a short explanation. The second stage is tool call format injection. We train the model on Tool-FAS 16K so it learns how to perform multi-turn reasoning, when to call tools, and how to use tool results to support the final decision. The third stage is diverse tool GRPO. In this stage, the model learns autonomous tool use from query label pairs. The reward function considers three aspects: the correctness of the fast answer, the correctness and format of the final reasoning, and the diversity of valid tool calls. This encourages the model not only to be accurate, but also to use appropriate and diverse tools during investigation. We evaluate TAR-FAS under a challenging 1 to 11 cross-domain protocol. The model is trained only on syllaba A spoof and tested on 11 different target datasets, including CASIA MFSD, replay attack, OULU-MPU, SIW, WMCA, hi-fi mask, and others. As shown in the table, TAR-FAS achieved 7.54% average HTER and 96.67 AUC, outperforming previous methods such as VitaFAS, VITL, FLIP, and IFAS. This demonstrates that tool-augmented reasoning can significantly improve cross-domain generalization, especially when the target domain contains unseen spoof materials or attack types. We further conduct ablation studies. First, we analyze different visual tools, starting from the zoom-in baseline. Adding frequency tools, texture tools, or structure tools all improves performance. When all tools are used together, the model achieves the best result, confirming that these tools provide complementary evidence. Second, we analyze the training stages. The results show that each stage is important. FAS knowledge transfer provides domain knowledge. Format injection teaches the model how to use tools, and DTG-RPO further improves autonomous tool selection and reasoning. Together, these results validate both the Tool-FAS 16K dataset and our tool-aware training strategy. Here we show several visualization examples. For a real face, TAR-FAS may use FFT, LBP, and HOG to confirm that there are no periodic artifacts, unnatural texture, or abnormal gradients. For print and replay attacks, the model often uses frequency tools to detect periodic patterns or screen artifacts. For mask attacks, it tends to use structure and texture tools to inspect unnatural boundaries and surface patterns. An important observation is that TAR-FAS can revise its initial prediction after tool-based investigation. This makes a decision more reliable and interpretable. To conclude, we propose TAR-FAS, a tool-augmented reasoning framework that reformulates face anti-spoofing as chain of thought with visual tools. We construct Tool-FAS 16K and introduce a tool-aware training pipeline with DTG-RPO. Extensive experiments show that our method achieves state-of-the-art cross-domain performance with interpretable visual investigation. Thank you for watching.